Hi everyone, and welcome to this 10th section of CS188. Today we are going to solve a problem thanks to particle filtering. So here we take the same problem as we had the previous week before spring break, and this time we expand the grid we have so that it becomes infinite. So now we study a location that is in z square, so a pair of integers, and we know that at each time step t, the J-bar which we're tracking is in a certain cell. And we also have an assumption about the dynamics. We know that with probability 0.5, it stays where it is. Otherwise, it goes to a neighboring cell at random. So now we no longer consider that it can teleport. In the first question, we are asked to write down the transition probability function that's associated with this assumption. So if you write it down, let's see what's the likelihood that we are at t plus 1 in a certain location, x prime, y prime, given that we were in another xy at the previous time step. So here we know that with probability 1/2 we can stay. We also know that with the probability 1/2 we can go to one of the 4 neighbors. This time we no longer have edges, so that's the other option, and 0 otherwise. So this you can rewrite as 1/2 times the indicator function in xy plus 1/8 the indicator function in x plus 1y plus the same thing in x minus 1y. So that's when we move left or right. And now we study the case in which we go up or down. And so the indicator function here is 1 if in x prime, y prime. Sorry, let me rewrite that. The indicator function xy in x prime, y prime is 1 if and only if x prime, y prime is exactly xy. Okay, so that's our transition probability, and that answers question A. Okay, so now we assume that we gather some information about our location that will give us an indication about the current longitude of z, and now we want to leverage the information so as to determine a certain likelihood over the actual location of the J-bar work. So the way we're going to do that in this problem is using particles. And we suppose here that we are at a certain time step t. We don't really care for now about what happened before, and we have 4 particles that have been compared to actual observations and given different weights, which are the evaluation of this likelihood function here for each particle. So if we assume that there is a certain x for a certain particle and we observe a value for r, we can use the corresponding probability to weigh the different particles. So these are likelihoods. And that's not exactly what we want. What we would like is a probability distribution that we can sample from. Probability. And therefore, the first thing that we're going to do is normalize with respect to the sum. So here, if we sum this up, we find 2.0. So if we divide now by 2.0, what we get is 0.125, same thing here, 0.5 and 0.25. So now we can use the random numbers that have been given to us so as to generate particles based on this probability distribution. So what we're going to do is order our particles, and here it's already done. And we are going to compute the cumulative density function for each. So we start at 0.125, that's the probability associated with the first particle. Then we add 0.125 to that, so we get 0.25. We add 0.5 to that, we get 0.75. And finally, we get 1. So now we're given different values for these random numbers, and the first one is 0.142. So that's where A1 is located. So we locate A1 on the density axis, we project it over the different particles, and we take a look at the first particle that gives us a cumulative density function higher than the value in A1. And this particle is P2. So now, as we resample, all the weight will be the same, but we'll have redundant particles. So the first one is P2. Then if we use A2, it's 0.522. So it hits in a P3. Then the next one is A3, 0.916. Sorry, let me use a different color. And the particle that it hits is P4. And the last random number given in the problem is 0.792, A4, and it also hits P4. So here, because of the randomness of the resampling scheme, we can see that in fact we get twice the particle P4, while it was not the most likely if we were trusting the likelihoods and the probability distribution that we had over the particles. So that's randomness that's inherent to the resampling scheme, and well, that means that in practice we'll have to use a large number of particles, specifically in high dimensional spaces. Okay, so we've resampled, we obtained new particles, and now they are all weighted identically. The only thing that will show that the state is considered more likely at the moment is that we have more particles corresponding to that state. Now let's do question C. So in C, we want to estimate a more complex conditional probability distribution. We want to have a probability distribution over a complete path, and each particle is going to cast a probability distribution over that as we track the path of the corresponding particle given a certain set of observations. So let's first study what we do at step t equals 1. So what we first do is we sample from the prior P of Z1. And here it's an even prior between two particles, between two states, sorry, 0, 0 and 1, 1. So if we use A1 now, the first value, A1, is below 0.5, so it means that A1 is going to give a particle in 0, 0, A2 is above 0.5, and therefore we'll obtain a particle in 1, 1. Now we observe. Now what we observe is that R1 is 1, so we can weigh the two particles. So 0, 0 will have a weight of 1 over 2 times 1 over 4, so 0.8, and the other particle will have a weight of 1/2 because it has a location x that exactly corresponds to 1. So once we've observed, we have weighted particles and we normalize, which prepares the sampling procedure and also gives an actual probability distribution over the different states. So we normalize, and the total weight here is 5/8. Therefore, and finally we resample. So now we use A5. This number is 0.036, and we compare it to 4/5. 4/5 is bigger, so it means that we get a particle in 0, 1. If we use A6, which is 0.859, it's going to hit 1, 1, where the cumulative probability distribution sums to 1. And that means that we get a particle in 0, 1, a particle in 1, 1. So that's for our current belief. And now finally, step t is 3. Well, we use the transition function again. So t3 is left, which means that 0, 1 will end up in minus 1, 1. The other particle will stay. So we'll have one particle in minus 1, 1, another one in 1, 1. Now, so we apply the transition here. Then we observe. And what we observe here is R3 is 1, which means that the first particle minus 1, 1 will have a very small likelihood of only 1/16, while the second one will have a likelihood of 1/2. Then we normalize, and this time we normalize by a different sum of weights. Finally, we resample, and this time we use the last two random numbers that have been provided in the problem. So A7 is 0.656. So the first thing it's going to hit is 1, 1, where the cumulative density function jumps to 1, while A8 is below 1/9, and so the first particle it will hit is minus 1, 1, and therefore in the end we'll sample these two particles with equal belief. So now let's track down how we've generated these particles. So 1, 1 here came from this particle here, which came from this transition here, which came from this resample particle here, which came from here, which came from this transition, which in turn came from this resampled particle. And for the other particle, we have a different path, which comes from this succession of resampling and transitions. So now if we track down the green path in terms of resampled particles, we have 1, 1, 0, 1, minus 1, 1. And the orange path is 1, 1, 1, 1, 1, 1. Therefore, here the probability, the conditional probability that we estimate is 1/2 for this path, and same thing for this other path. The conditional is also 1/2. So that's the posterior we obtain over the path. Okay, so now that we have that, we have only two trajectories here. In theory, in practice, when you have just a quick correction here. In fact, this arrow is not good to this particle, because in fact it didn't have any child particle
this particle here in green comes from the same parent. So here, what we can notice is that we lost the information that was entailed in the particle 0, 0 because it was not sampled at all. Okay, so now that we've sampled this path, we can answer a couple more questions. The first one is about evaluating the posterior probability that at the third time step we have x3 is different from y3. So let's just recall the two paths that we sampled. The first one is 1, 1, 0, 1, minus 1, 1, while the second one, the second path is 1, 1, 1, 1, 1, 1. So that's the trajectories that we've simulated by tracking down the lineage of our particles. So now we have a weight of 0.5 on the first path, 0.5 on the other one, and there's only one path that has this property of having a longitude that's different from the latitude at the last time step. So the probability we're looking for is 1/2. Now, we are asked to compute the expected number of distinct x coordinates visited by the Jabberwock, and here, let's just take a look at the different numbers for each path. So we'll have 1/2 because each path is equally likely. On the first path, we explore 3 different x coordinates, while on the second one, we only have 1. And that means that the expectation here in terms of number of different x coordinates explored is 2. And that's just an estimate with the 2 samples that we've obtained here. In practice, we would need way many more particles to have a more reliable estimate. So what about the probability that we return to the starting point? Well, the starting point is 1, 1, and there's only one path that returns there, so the probability is 1/2. And finally, G, what if we use weighted particles? How would that change our results? Well, we could absolutely forget about the last rebalanced weight we obtained after resampling and keep the weight we obtained for our path. And it means that the weights we would have are no longer 1/2, they would be 1/9 and 8/9. So that changes a couple of things. Typically, the estimate that of the probability that x3 is different from y3 now is 1/9. And if we want to recompute the average number of different x coordinates visited, we would have to use the same weighing scheme. So here, that's what weighing would change in terms of estimating these quantities of interest. Could we use the elimination algorithm to compute this quantity? Well, the reason why we used particle filtering here is mainly because we are dealing with an infinite state space. So here it's a 2-dimensional state space, and that's exactly the kind of setting in which we would have a lot of issues trying to use the elimination algorithm, which inherently assumes that we have only a limited number of states. So here we could get away with a simple remark. After n steps, well, we can only be in 2n states. So we could restrict our exploration to a finite number of states using this particle trick. However, as compared to particle filtering, this would be much slower because very quickly we'll have to compute over very large vectors. Particle filtering is not perfect, however, here, well, it would work if we were using more particles because we only have 2 dimensions to our state space, but quickly as you add dimensions to your state space, the particle filtering scheme collapses. So you have to use other methods.